Hello, welcome to Byju's JEE, another of our live sessions, and today we are going to talk about optics. Now, optics is a pretty independent unit on its own, in the sense that if you are beginning the study of optics, although it is in 12th standard, you can also do it in 11th standard because it doesn't have great many prerequisites, and it has a style of its own. Okay, and to whatever extent I have gone to the depths of optics, I would say that this whole study of optics, the study of light, has more to do with precision than with actual too much thinking. Okay, so you get all the formulas right, and you understand the formula in the context of a diagram, and be very precise when you're calculating. So what I do is, like, if my normal speed of solving a problem is, let's say, x, my speed of solving an optics problem goes like by like 0.6x, or like half of it, like 0.5x. okay, so I have to become very careful, I know, when I'm solving an optics problem, because it is very calculative, and I feel that you can go wrong in one small step and everything will get screwed up. Okay, so don't do that. Now, optics is a very big chapter. All right, it is almost of the size of mechanics, almost of the size of, not mechanics, mechanics is too big, almost of the size of electrostatics. Now, what does optics has? So basically, the broad classification of things we are going to learn in optics has to do only with reflection and refraction. That's the only two things. Reflection is when a light beam is reflected from surface, it means that it is returned to the same medium, and refracted is when a light beam moves from one medium to another medium, and we know that here we have an assumption that light travels in a straight line like a ray. Now, reflection itself is divided into two parts: reflection at plane surfaces, then reflection at curved surfaces. Reflection at curved surfaces is what we call as mirrors. So plane mirrors and curved mirrors are the two parts of reflection. Then in refraction, you have many divisions. Refraction at plane surfaces, which is like a glass slab or something. Then you have reflection through a prism. Then you have reflection at curved surfaces, and then again curved surfaces, thin curved surface, that is like a lens. Okay, and in the end we'll talk a little bit about wave optics. Okay, so let's start. Reflection at a plane surface. Now, the first thing which is expected from you is that, let me use my phone as a prop here. So let's say this is a plane surface and you have an object here. They ask where would be the image. So what you have to do is you have to draw a perpendicular from this point object to the mirror. Okay, you draw a perpendicular and use the idea of plane mirror that object distance is equal to image distance. Okay, so the distance of the object, if let's say it is x, the image distance will also be at a distance x in the same line. Okay, so from the object to the image, the line which joins them has to be perpendicular to the mirror. Okay, then you'd be able to like find exactly where the image would fall, first thing. And I've already told you that image distance is equal to object distance. And we have a phenomena called lateral inversion in case of a plane mirror. Now, a general question which is asked, which you might have seen here, is when you have two mirrors and they are inclined at an angle, say at an angle of theta or something, and you are expected to tell how many images would be formed. Okay, so in that case there's a direct formula, and there's also a very good method to visualize it, which we have dealt in our videos. So do check out the videos, but I'll tell you the formula in brief because this is obviously a brief session. So between the two mirrors, if the angle is theta, then what you do is you find a number called n, which is 360 divided by theta. And if this number 360 divided by theta, where theta also you have kept in degrees, please be careful, don't keep it in radians, because this 360 has come from 360 degrees. Then you get this number n, and if this number n happens to be an even number, then the number of images that will be formed will be n minus 1. Basically what happens is that space gets divided into n different parts. Okay, it's a very beautiful visualization for this. And if this number n happens to be an odd number, then the number of images formed is equal to n itself. Okay, so that is one formula which we have here. The other thing which we are concerned is if the object starts moving with respect to the image, so with respect to the mirror with a velocity vom, then the image also starts moving with respect to mirror but in the opposite direction, but with the same speed. So V object with respect to the mirror is equal to minus of V image with respect to the mirror. Okay. Then we see refraction at plane surfaces, that is at a slab. The basic idea of refraction is that when a light ray goes from a rarer medium to a denser medium, it bends towards the normal, and when it goes from a denser medium to a rarer medium, it bends away from the normal, right? So denser to rarer, D to R away, and R to D towards the normal. Okay. So how do you deal with this? So see, in case of reflection, we had this laws of reflection, that angle of incidence is equal to angle of reflection. It's so famous that I almost forgot mentioning that. But in case of refraction also, you have a law which connects the angle of incidence to the angle of refraction. Okay. This law is called the Snell's law, and which is the way we define it is like the many ways to express it, but either way I express it, let's say, is mu1 sine I is equal to mu2 sine R, right? Mu1 is the refractive index of medium 1 into sine I, which is the angle of incidence or the angle in that medium. So refractive index of a medium times the angle of that medium equals to refractive index of the other medium times the angle of the other medium, which is could be the angle of refraction, or and that number is the refractive index of that medium. So for different medium, the denominator will change, right? And obviously we know that the speed of light is maximum in the vacuum. So in a medium, its speed is going to be only less, right? In that case, we realize that mu is always going to be greater than 1, except for in vacuum when it is actually equal to 1. Now that is the refractive index. Now here there is a phenomena which we see in refraction, which is called total internal reflection, and there is another word related to it which is called as critical angle. Now you see, if a light ray is going from a denser medium to a rarer medium, now you have to imagine everything. Imagination is as important as, I would say, animation. So when a light ray is going from a denser medium to a rarer medium, what happens is that you see that the angle with the normal is increasing, right? Because it is bending away from the normal. So as you keep on increasing the angle of incidence in the denser medium, what will happen in the rarer medium is that it will move even far and far and far. So there's a particular angle in the denser medium for which what happens, the ray in the rarer medium has already become 90 degrees. Okay. So this angle in the denser medium for which the ray in the rarer medium has become 90 degrees, right? That is, the angle of refraction has become 90 degrees. We call that angle as the critical angle. It is a critical angle because what happens is, after this angle, once you cross this angle in the denser medium, there is no more refraction and the entire lights get reflected. Okay. When I say entire light, it means that there is very, very less absorption and almost no refraction. There is totally reflection. Okay. So there is very less loss of data, in the sense that we use electromagnetic radiations, that is light, to transmit data. So every time it hits something, some amount of that data, its amplitude gets reduced. So we use optic fibers where basically we transmit this data using the total internal reflection, because what happens in total internal reflection, as the name suggests, it is totally internally reflecting. The total reflection happens and very slight absorption happens. So that is why it is it's not called total because of just a random reason. It has a very significant reason, that it is because in a normal mirror, when you see something reflecting, the light is also refracting. Okay, but here it is completely reflecting. Okay, now we have, okay, and focus is defined as, if you let some parallel rays shine on this mirror, the point where all the rays meet is called the focus. Okay, so F is equal to R by 2, and again, the interesting thing is, I think I should discuss this, is the sign convention. So let's say this is your, although it is straight, but you can imagine it to be a curved mirror. So if it's a curved mirror and the light ray is coming from this end, we have to be very careful about what your V and U is. U is called the image distance, U is called the object distance and V is called the image distance, and we have to use that in that formula with the sign convention. Okay, so how do you figure out the sign convention? So if this is the incident ray, So direction to which the incident ray is going, which is this direction, is always positive. Okay, and so the other direction becomes negative. So this is negative, that is positive. All right, and that's it. So if this is a concave mirror, right, which is caved, the reflecting surface is caved, the focus lies on the negative side. So F will also be negative in that formula. And if it's a convex mirror where the reflecting surface is vexed, in that case the focus is on the other side and F value becomes positive. Okay, so all these things have to be taken care of, especially the sign convention here. So I've spoken about critical angle. Let's talk about refraction at a curved surface. The famous formula you have, mu 2 by V. I don't think it's that famous, but yeah, people tend to usually forget it. Mu 2 by V minus mu 1 by U equals to mu 2 minus mu 1 by R is the formula, and people make a lot of mistake while applying this formula, because the reason is that they get confused with what is mu 2, what is mu 1, and again the sign convention. Okay, so again the same thing, if you have a curved surface, right, and a light beam is coming from here, so the region or the medium in which the incident rays lie is number 1, okay, and the other one is numbered 2. So when I say mu 2 by V, mu 2 is the refractive index of the medium where the refracted ray is lying. Okay, mu 2 divided by V, right, with the sign convention, minus mu 1 where the incident ray lies divided by U equals to mu 2 minus mu 1 by R. R is the curvature or the radius of curvature of that curved surface, and it also has to be kept with the sign. So sign convention has to be followed all the way through. So especially when you get questions where you have a sphere or a bubble and or like a paperweight or something, and there's an object on this side and you have to find where the image will form. So in those cases we use refraction at curved surfaces, and especially for a sphere that refraction would be happening twice. So you have to use the same formula twice, and every time the meaning of mu 1 and mu 2 would change. So every time you are using this formula, or actually any formula in optics, you have to be very careful in this formula. What is my 1, what is my 2, what is my positive, what is my negative? What is my 1, what is my 2, what is my positive, what is my negative? Okay, you have to be very careful about that. So the next kind of thing which we saw in the refraction was lenses. Okay, so this like mirrors, in lenses also we have this formula, but there's a small change. Instead of 1 by V plus 1 by U equals to 1 by F, we have 1 by V minus 1 by U equals to 1 by F. Okay, and things are not so easy here. F is not equal to R by 2 for a lens. Please remember that. For a mirror, F is equal to, for a curved mirror, F is equal to R by 2, but for a lens, F is not equal to R by 2. In fact, there's a whole new formula to find the focal length. Okay, but again, to define focus, what will it be? If you shine some parallel rays to the lens, the point where the rays converge or appear to converge is the focus. Again, the definition is the same, but the formula changes. Again here, F is equal to mu 2 by mu 1 minus 1 1 by R1 minus 1 by R2. Now in this case you would say that mu 1 and mu 2 are both same, because the light is again going to the same medium. So you have to see it in this way. Not see, this is the lens, right? So your mu 2 is where the refracted ray is arising from. Okay, so your mu 1 is air and your mu 2 would be the glass inside which the refracted ray first comes to, because after that it again goes to air, and what we are using here is a combination of two curved surfaces. So be careful. In case of lens, by mu 2 I mean the inside part of a lens. That's how you should remember. Mu 2 is the inside part of the lens and mu 1 is the outside part of the lens, right? Because that is what it is going to be. Because the incident ray is always going to be on the outside part of the lens. Okay, and R1 and R2 are the two radius of curvature we have, the radii of curvature. R1 for this end and R2 for the other end, and again you have to use it with the sign convention, and when you plug it all in, you can use this formula very carefully. So let me remind you again that optics is a subject of precision. Okay, so if you do even a small mistake in the sign convention or forgetting something, then all your knowledge would be almost of waste, because you not come to the final result. Then we have the idea of a prism. A prism is basically like a construction which has three rectangular sides and two triangular sides, okay, and the topmost, so if this is a prism, you imagine this to be a triangular prism, then these two surfaces are called your reflecting surfaces, or sorry, your refracting surfaces, from where you actually shine the light and see things going. And this angle which it makes on the top is called as the angle of the prism. Now what happens is that when you shine a light, it's a general rule that if the refractive index of the prism is more than that of the surrounding, which is usually the case, 99% of the case which you deal, the light ray is always deflected or deviated towards the base of that prism. So no matter where the light is coming from, it will always go towards the base. By what angle will it go, that will depend on the angle of the prism and the material of the prism and all that, okay. So in a prism, basically refraction is happening, and the angle of the prism is equal to R1 plus R2, where R1 and R2 are the two angles of refraction that we have. So when you have a prism, you are having a refraction over here, and again a refraction over here. So the inside angles, okay, this is the angle R1, this is the angle R2. So basically R1 is the angle of refraction for the first time, and R2 is the angle of incidence for the second time, but we call them R1 and R2 because they are both the inward angle, right? I'm leaving a lot of things to you for your imagination, I understand, but this is basically a quick revision, so I think I'm allowed to do that. So A equals to R1 plus R2, and then delta, which is basically the deviation of this ray, is given by I1 plus I2 minus A. Okay, I1 and I2 are the two angles of incidence on the outermost on the outer sides of the prism, like when the ray strikes and when the ray goes out. I2 is also called as the angle of emergence. Now in prism we especially learn a condition called as the condition of minimum deviation. The condition of minimum deviation happens, remember this, it happens when I1 becomes equal to I2, right? When I1 becomes equal to I2, you have a condition of minimum deviation, and in that case you will have A equals to 2I, delta is equal to 2I minus A, because delta was equal to I1 plus I2 minus A, so instead of I1 plus I2 you have 2I minus A, right? And from there you can derive whole lots of formulae. Then another thing of our interest is a thin prism. So what happens in a thin prism is there are some approximations that we make, and the basic thing which is there in a thin prism is that the deviation which a thin prism produces is mu minus 1 times A, okay, where mu is the refractive index of that prism and A is the angle of the prism, okay. Now so till now we were discussing about when you shine a monochromatic light into a prism, you can also shine a light which is a combination of many wavelengths, like white light, which the one which comes from sun. So what happens so the refractive index of the medium, right, is different for every wavelength, okay, because the speed of every wavelength inside a material would change because the frequency is different, right? So the refractive index and of every wavelength is going to be different. So red has a different refractive index and violet has a different refractive index. In fact, the more the wavelength you have, the lesser is the refractive index you have. So red has the least refractive index for a medium, and so that is why red gets deflected or deviated the least, okay, and violet has the maximum has a minimum wavelength, so it has the maximum deviation, okay. And that is why, because these deviations are varying, what happens when you see on the other end you shine a white light, but if it's a combination of different wavelengths, and for different wavelengths you have different refractive indices, so what happens on the other side, they get deviated by different amounts and you see a band coming out instead of that white light again. So you see a spectrum coming out on the other end, red on the top and violet on the bottom, okay. Again, for this spectrum, a deviation is defined, which is the deviation of the middle, the yellow line, which is defined as to be the deviation of the yellow line, the yellow wavelength I mean, and that will be equal to, delta is equal to mu y minus 1 into A, assuming that it's a thin prism. And then there's something called as the angle of dispersion, which is defined here, which If you take the violet line and the red line, and if you try to join them back, they form an angle. So they are like diverging. They are not parallel. Okay. So the angle which they form is called as the angle of dispersion, and is given by mu 1 minus 1 by mu into t. And no matter how many glass slabs you have, and whatever is the gap between them, immaterial of the gap, like irrespective of the gap between them, and the placing of the slabs, on the other end, the displacement, the amount by which this initial object appears displaced from its initial position, is just given by the shift because of the addition of shift because of all the slabs. That is, if the first one is creating a shift of say S1, and the other one is creating a shift of S2, and the third one is creating a shift of S3, the total shift that you'd observe on the other side will be S1 plus S2 plus S3, and this will not depend on where the slabs are placed. No matter how you place it, you're going to observe the image shifted by the same amount. Okay. Another idea is apparent depth and actual depth. So whenever you are on the rarer medium and you see something on the denser medium, it appears closer. And whenever you are on a denser medium, you look at the things in the rarer medium, it appears far away. So the way I remember it is the fish and the man example. So I remember that whenever I look at a fish inside a pond, it appears little elevated than it actually is. It appears above than its actual depth. Okay. So and when a fish would look at me, I would appear farther than I actually am to the fish. Okay. So when you are in a denser medium, the things on the rarer medium appears to be far off, and when you are in the rarer medium, the things in the denser medium appears closer. Okay. And there's a simple formula. Actual depth equals to apparent depth, or you can say apparent depth is equal to actual depth. Either you multiply mu or you divide mu. Okay. So whether you will multiply mu or you will divide mu will depend on where you are. So for example, I am in denser medium looking at things in the rarer medium. So I know that it is going to appear far than it actually is. So apparent depth is equal to actual depth into mu, because mu is a number greater than 1. So it is going to increase. I already know that. And if I were a man looking at a fish, then apparent depth would be actual depth, because it will appear closer. No, depth will reduce. So apparent depth is equal to actual depth divided by mu. I'll do that. So this is the way I remember this formula and its application. By the way, this depth is always measured. This thing, from where are we measuring this apparent depth and actual depth? This is always measured from the interface, right? There will be an interface, that is the boundary between these two mediums. So always measure it from the boundary. This is a mistake which students do very commonly. Okay. So this is geometrical optics. Now let's talk a little bit about wave optics. In wave optics, basically the major thing which you have is the Young's double slit experiment. I would suggest you to properly remember the setup of the Young's double slit experiment. The two slits, the gap between the two slits is called D, and there's a screen. The distance of the slit plane from the screen is capital D, and between the two slits you draw a line from the middle, the perpendicular line which cuts both the screens perpendicularly, and at that center you get the central maxima, and then you get bright fringe, dark fringe, bright fringe, dark fringe. Okay, like that. And you find that the path difference is given by d sine theta, right, where theta is the angle from the center of this to any particular point wherever you want to find, whether it's whatever is the path difference at a point on the screen. So I remember this because there are a lot of formula in this chapter and I keep forgetting. So see, every time I try to recall, I just recall two things. One thing, path difference is given by d sine theta. Cool. Second thing, this sine theta is approximated to be y by d, y by capital D. Y by capital D basically will give you tan theta, but tan theta, because theta is small, is equal to theta, that is equal to sine theta. So that sin we have done, okay, of approximating it to be equal to tan theta. So d sine theta is the path difference, and d sine theta and sine theta is equal to y by d. So d times y by capital D becomes equal to n lambda, this I know, whenever there is a constructive interference, and 2n plus 1 lambda by 2 whenever there is a destructive interference. Okay, so this constructive interference, destructive interference is something not new to optics. It is there in waves, it is there in sound, it is there in this chapter also. So something you really need to learn, that whenever two waves actually like completely crest to crest and trough to trough overlap, you have a constructive interference, and when they overlap phased out by a phase of pi, then you have a destructive interference. And Yeah, so part difference in case of constructive interference is n lambda, because even multiples of lambda it has changed, and in destructive interference it has changed by an odd multiple of lambda by 2. So when you do that, you get this formula that y is equal to n times lambda capital D by small d. So this is for all the bright fringes, and for the dark fringes you just replace d sin theta equals to 2n plus 1 lambda by 2. So you get the y for all the destructive interferences also. Remember, this lambda changes with the medium. So sometimes you are asked a question where this whole setup is immersed inside a liquid. In that case, lambda becomes lambda by mu, okay, where mu is the refractive index of that medium. And also this formula is valid only for a monochromatic light, because there's only one lambda we are talking about. When you have more than one lambda, you'd see different colors and different bright fringes and dark fringes of those colors. So when you actually do it in white light, you see multiple colors in that. But the central bright maximum will still be at the same point, because always at the center point you would have a path difference equal to 0, because both the rays are covering the same path to reach the center. So we have seen all these things in geometrical optics and wave optics, and I hope this session was helpful to you, and I think now we are ready to take some questions. Okay, fine. So Abmir is asking, sir, what type of questions or topics should we focus in optics for boards? See, for boards, I'll tell you, they'll ask some simple derivations, and you have to always draw a diagram, and don't forget to draw a ray diagram very properly with marking all the arrows and everything. And for boards, I would say they ask derivations, and they would ask you the derivation of finding the formula 1 by v plus 1 by u is equal to 1 by f, and very simple numericals. Okay, yeah, those kind of questions you can expect for boards. Sahil is asking, sir, while seeing in a mirror we see that a person's velocity doubles. What is the reason? What kind of mirror are you talking about, Sahil, here? If you have a plane mirror, then the velocity of the person doesn't double. In case of a convex or a concave mirror, the velocity might double, and I'll tell you a method to find the velocity, because I don't remember that formula. Nobody has to remember that formula. Okay, 1 by v plus 1 by u is equal to 1 by f. You have, right? You know, v is the distance of the image from the mirror, the relative distance of the image from the mirror, right? And u is the distance of the object from the mirror, and f is the focal length, that is a fixed distance. Now you differentiate this with respect to time on both the ends. 1 by f, the RHS becomes 0. You get dv by dt and du by dt. dv by dt will be the velocity of the image with respect to the mirror. Du by dt will be the velocity of object with respect to the mirror. You'd arrive at a formula for how the velocities would change. Okay, so it doesn't always double. Okay, it depends on what is the value of u, what is the value of v. At different positions it will change. Sweta is asking, list some applications of internal reflection, sir. I told that optic nerve, optic fibers is one application, which is one of the major applications of total internal reflection, because in total internal reflection what happens is that the information loss is minimum. So in optical fibers we use it. Mira is asking one more question, sir. In lateral inversion, the left side of an object appears to be the right side of the image, and vice versa. Why doesn't the top of the object become the bottom of the image? That is a very good question. Why doesn't the top of the object become the bottom of the? I think it has something to do with the way you look at the thing. Okay, because if you are standing this way and this is appearing here and that is appearing here, that doesn't just have something to do with the mirror, but also to the way your eyes are placed. Because if you look at the mirror this way, then you would see the lateral inversion happening in this. For example, this is the mirror, right? You imagine this is the mirror. We would say that mirror inverts thing across this axis. That's not true, because if you look at this way, then you would know that the mirror also inverts thing about this axis. So it has to do with the way your eyes are placed. In fact, in H.C. Verma, I think in this chapter, I think in the first 4 or 5 questions, there's one question which basically tackles this idea. I think you should try to solve that problem. Yeah, so these were some questions, and I hope I was able to answer some of them. Thank you for joining us on this live session, and I'm sorry that we got a bit late. Please go through our YouTube channel. We have a lot of interesting videos, and especially a chapter like optics, which has to do with light, must be dealt in a more visual way than like this, where, like, I'm just trying to compensate light with sound. And please do download our app, where you can find the whole chapter, and especially now that your boards are close by, I think it will be of great use to you, because you don't have a teacher now. You can't go to a teacher all the time. You can watch the videos again and again, and you can post questions, and everything has been like very clearly been visualized and animated and done there. Okay, so with that, thank you.